Hello, and welcome to our discussion and analysis on smart factories in the automotive industry. My name is John, and I'm joined by Quang, Calvin Thomas, and Calvin Zhang. In this presentation, we will discuss the history and development of smart factories. In addition, we will discuss our own case studies of smart factories in three distinct geographic locations: North America, Europe, and Asia. We will conclude with a discussion of our findings. Smart factories are, in essence, a highly digitized production facility. Smart factories are the combination of advanced computing, machine learning, smart robotics, and complex data storage systems. All of these systems work together to create a virtually fully autonomous production line. The first mention of the term smart factory was in 2011 at the Hanover Fair, a trade convention in Hanover, Germany. From there, smart factory development and popularity exploded with the advent of smart transportation in products like Tesla's smart self-driving cars. Smart factories, however, did not come out of nowhere. Automation and computer integration in manufacturing came long before first Tesla rolled out of the factory. Now we will give some background information on the history and development of smart factories. The history of smart factories is rooted in the history of automation, which first began to take shape in the early 20th century on the factory floors of automotive companies like the Ford Motor Company. In 1913, Henry Ford developed the moving assembly line, which would forever change the way products were manufactured. The genius behind this new method developed by Ford was to bring work to the workers instead of having workers go to their work. This new process allowed for vastly increased production rates and allowed Ford to decrease the price of their product, increasing sales. Workers focused on developing one single piece of the car that they would add and continue this process over and over for each car that passed them on the line. The similarities here between the Ford moving assembly line and smart factory development can be seen quite easily. One human worker developing one part quickly transitioned over the 20th century into a robotic worker doing the same in the 21st. From early automation, a rapid development would swoop over the manufacturing world in the mid-1900s with the development of new production line control methods. Automation in manufacturing would see another explosion in development following the so-called Third Industrial Revolution, which occurred during the mid-1900s. This period of innovation ushered in advanced computing technologies. Technologies like programmable logic controllers, invented in the mid-1960s, allowed for greater remote control of manufacturing lines. Before PLCs, manual relays were largely responsible for the immense task of controlling these advanced industrial applications. Relays rely on a hardware system that, while reliable, are not flexible and struggle with ever-changing manufacturing requirements. PLCs, on the other hand, are digital, which enables engineers and technicians the ability to quickly make programming adjustments and see immediate changes. Now, almost 75 years later, PLCs continue to see use in factories and have laid the groundwork for advanced computer control in smart factories. The final stage to be examined in the history and development of smart factories is the so-called Fourth Industrial Revolution, where we currently stand today. This level of manufacturing innovation and development represents the full use of computer technology to create full task automation. Robotics are now capable of handling advanced human tasks that require independent decision-making. Crucial to this development is the implementation of robotic intelligence gathering called machine learning. Machine learning is seen as the most fundamental function in the advancement of artificial intelligence and smart computing. This continues into smart factories. Building a factory that continually becomes smarter and more efficient over its lifetime is the ideal growth production model for any manufacturing business. In addition, new advances in data storage technology allows for massive amounts of data information to be stored, streamed, and transferred with extreme speed and efficiency. This allows for a more interconnected facility that can literally talk to itself, speeding up part production while simultaneously reducing waste. Smart factories will serve as a cornerstone and model for factories and manufacturing for the foreseeable future.
The automotive industry has had an increasing need for implementation of new methods and technologies that can handle recent problems for automakers. Continued safety violations and employee endangerment has been an increasing problem with the rising demands for automobiles and automobiles that are more sophisticated. Right now, the demand for cars is still high as the pandemic mindset relaxes and people venture back out into the world. Not only does the demand for cars remain, but the speed of this changing demand is high. Production needs need to be fast. Employees operating new heavy machinery is far more dangerous and results in automakers needing to deliver compensations and paid leaves for workers often. Companies are losing more money than they'd like to, and costs are being translated to customers. COVID has also brought about new complications for automakers regarding remote work and the dwindling labor supply. More and more employees are looking to work remote, and technician and engineering jobs in a lot of automotive facilities cannot be remote as much as other types of jobs. On top of these aspects are increased complexities of products that need more precision than human coordination, especially with electronics and advanced vehicular systems. With this complexity comes more room for error or defects that are undesirable, both consumers and producers. So any way that this shortcoming can be mitigated is needed for automotive manufacturers. Smart factories, or the implementation of smart manufacturing into automotive factories, is the route that automakers are taking to fix all these issues.
We will now discuss our case study analysis in North America, Europe, and Asia. The first case study will be diving into North America's approach to integrating smart factories and how it has affected the specific motor industries. For this study, we will be looking into Ford Motor Company. Ford has always been known for the willingness to adapt and implement new technologies as well as be a part of the new innovation. Some of these new and upcoming technologies that Ford will be implementing are 3D printing in their advanced manufacturing center, artificial intelligence in the Ford transmission plant, and 5G network in their electric vehicle center in Michigan. To integrate a better manufacturing system, they implemented the Ford automation software template, FAST. FAST created a digital template to standardize process softwares, process configurations, and quality monitoring. This allowed for plants all over the world to use a singular system that can be updated and adjusted as one. A critical aspect of FAST is the software process configuration tool. This allows for centralized access to every assembly station as well as the recipe being used to assemble parts. Another system that was put into place was the global parts tracking system. This system worked with the FAST to track parts throughout the plant. Each part was given a 2D matrix code and is scanned when it enters each cell. This tells the system exactly which cell this part has been to and which gantry it has crossed. GPTS allows for better error detection and problem identification through the tracking logs. 3D printing is one of the many new advancements in smart factories in the last few years. Ford has begun rigorous testing of 3D printing in the new Advanced Manufacturing Center. This center houses 23 3D printers that are from 10 different additive manufacturing companies, including HP and EOS. Along with that, Ford has now slowly started implementing these 3D printed parts into the high-end cars. On the right, you can see Harold Shears, Ford's technical leader as the Advanced Manufacturing Center. He's holding the 3D printed bracket that holds the brake line for the 2019 Ford Shelby GT500 Mustang. In recent years, Ford has invested a lot of time and money into developing artificial intelligence in their robots. They've collaborated with Simbo Robots, which is an AI company that specializes in implementing AI in industrial robots to outperform the status quo. Example of this within the Ford transmission plant in Michigan. Within this plant, AI is integrated within its robots, such as the one shown above, for assembling torque converters. The AI program analysis the last 100 attempts to learn how it maximizes the efficiency of each movement. Data has shown that the AI has allowed this section of the manufacturing plant to operate 15% faster. 5G will be integrated in their electric vehicle center in charge of producing the new 2022 Lightning Ford F-150. 5G allows for ultra-high speeds, extreme low latencies, and massive connectivity. The faster network allows for the employees on the production line to use tablet computers to send and receive information about equipment status. The machine and automated robots will be equipped with 5G networks to allow for high volume data transfer for real-time data capture and analysis. This will allow for instant feedback and fast reaction times between the machines and control systems. The cloud will also allow for remote expert support, and more importantly, it opens the door to AI technologies and using them towards improving precision, efficiency, and safety.
In Europe, several organizations are adopting smart factories into their company and business model as not only a way to better their products, but also survive among the competition. Volkswagen has created an industrial cloud that provides the utmost interconnectivity between their facilities. The industrial cloud works by integrating data on every level and relaying this data to a processing platform that can interpret it. Everything from the integrated robotics on the shop floor to the conveyor belts and to the material transportation are monitored for correctness and timeliness. This helps communicate to other integrated components about the schedule and processes so that production lines can operate properly when needed and without the manual input of workers. The cloud also relies on an artificial intelligence that crunches all the data and can digest it to recognize issues in production or errors along the way that need human intervention. The artificial intelligence also works by self-enhancing the manufacturing processes and determines points of inefficiency and can change the timing or schedule of automated machines. The data gathered from the AI is also put into sophisticated models that can help inform the management about long-term operations productivity and the lifetime of robotics. The integration of this technology has been very beneficial for Volkswagen and has proven to improve the changeover speed of various production lines as well as maintenance. The BMW Group has taken a tech-heavy approach to smart factories, and the way in which they have changed their production is to increase speed, efficiency, safety, and complexity. BMW has fully automated much of their more menial tasks that are not too sophisticated, such as part transfer and equipment change. BMW utilizes autonomous trains and transfer bots that move various materials across the BMW facilities. This saves time and man-hours for the company, allowing employees to focus more on the skilled work that humans perform. The facilities that BMW owns are also relying more on heavy interconnectivity, similar to Volkswagen, which communicates with a wide array of machines and other facilities to ensure the autonomous robotics are coherent together. On top of this, the software in place that connects all these components operates on machine learning algorithms that help to adapt the system for changing production operations. The software relies heavily on real-time data that is accumulated from countless sensors on machines and robots, which constantly take information regarding the performance of the element. Finally, BMW has also began using exoskeletons as a way to boost worker performances by allowing them to carry more weight and perform certain tasks for longer with the support of this exoskeleton. Tesla, an American company, has a new European facility in Germany that has been coined the Gigafactory. This facility is new and the epitome of a smart factory in the way in which it is powered, operated, and incorporated into manufacturing. The Gigafactory has its own on-site transportation system that not only moves employees from various parts across Germany, but also different parts of the factory. This increases employee integration into the company and ensures that they can partake in their duties. The facility is also very sustainable and is powered by solar arrays located on the factory roof itself. Sustainability is an aspect of smart factories that more and more companies are turning to. Tesla's Gigafactory is also one of the few car factories that makes their own batteries. The Gigafactory is not just a car factory, but an innovative technology facility.
Our choice of case study in the Asia region is Toyota. Toyota is one of the leading automobile manufacturers in the world, and they have been constantly developing their manufacturing strategy and technology to meet the growing demands across the world, as well as maintaining the high quality products, which has been star principle of Toyota since its founding day. Instead of going into the new technology, we're going to take a look at their core foundation, which is the Toyota Production System, TPS, management concept that have been widely recognized and studied across the world. TPS set the foundation for Toyota automation migrations and modern smart manufacturing. The diagram above is the house of Toyota Production System, which is a combination of the just-in-time system, the column on the left, and Jidoka, the column on the right. Just-in-time system was derived from a comment by the Toyota founder, Kiichiro Toyota, which was the best way to gather automotive part is just in time, establishing Toyota pull system of production. Jidoka, which can loosely translate it as automation with a human touch, was created by Sakichi Toyota during his time researching automation development. Jidoka involved stopping the process automatically when production went wrong, error preventing, and total productive maintenance for quality. Into Toyota development timeline. In 1940s and 1950s, facing the post-war effects and the collapsing economic system, Toyota needed to adapt to raise the productivity level to get large volumes productions. Their first pull system of productions was adapted in 1948, a foundation for the future GIT just-in-time system. In 1960, Toyota promoted mechanizations and conveyor belt system to produce only parts that are necessary. This marked the very first step of Toyota in their automation migration effort. Simultaneously, Toyota also launched a TPS implementation program across all plants in 1960. In 1976 and 1963, they adopted both continuous flow production system and concurrent multiple processes. In 1966, they created the first automated engine making line with transportation line at the Camigo plant. In 1970s and 1978, the company production level was raised tremendously through appropriate manufacturing strategy and careful planning with high precision machines. Toyota started to develop various type automated machines to facilitate higher production rate. This marked the late second phase of the Toyota migration automation strategy, aiming toward their fully automated production system and smart manufacturing in the next 20 years. In 1990s, While ramping up their globalization manufacturing network, Toyota started to introduce into their production system automated part supplier mechanism to flexibility meet the requirement of just-in-time theory. They also adopted the TPS practice into different culture in conjunction with their globalization scheme, with various innovation being introduced to local suppliers and companies. In 2000, Toyota added the newest addition of technology, Compass, which will be discussed later as their stepping stone into the age of smart factory. So below is the Toyota TPS plan, which take into production order and apply the just-in-time system to retrieve parts from the Kanban order system, created a timely productions through body processing, painting, assembly, and shipping out to customer. In the beginning of 2000s, Toyota added the newest addition technology, Compass, a system that stored the time and part location in data table to determine the shortest point-to-point distance in order to adjust the process due to errors or design change in smart factory. This was a concluding step of Toyota automation development and integral technology for the soon-to-be integrated smart factory in the 21st century. With their experiences in manufacturing since 1930s, Toyota quickly realized that current automation system can be improved drastically with not only the Compass, but also the implementation of IoT, Internet of Things, and cloud-based system. They made remarkable progress in adapting real-time data collections and data analytics to support their lean system and amplify Kaizen while conforming to their TPS principle. Partnering with multiple Japanese new tech company, manufacturing giant Toyota will be able to combine the power of artificial intelligence and big data analysis on their already established automated manufacturing floors. The picture above is their automated assembly system at Toyota City, Japan. Around the late, well, we're going to discuss about their economic growth since the implications of TPS. Around late 1950s and early 1960s, the TPS implementation started to run at Toyota plants. Toyota started reaching the production rate of 100,000 vehicles annually for first time in history. Production, particularly in Japan, expanded rapidly during motorization in 1960, and Toyota finally surpassed the domestic production rate of 1 million vehicles around 1968. The Compass system, alongside with tremendous effort in automation integrations, had helped to stabilize the company domestic production around 4 million vehicles per year. Simultaneously, Toyota also placed heavily emphasis on their globalization manufacturing. In 1970s and 1980s, the overseas production rate reached 100,000 vehicle mark. Consequently, when the mass production in United States started in 1984, international local production make dramatic advances, reaching 1,000 mark in 1994. As Toyota increased the manufacturing influence globally and stabilized their domestic production rate, the combined production number reached 8 million vehicles made annually in 2006. In the last recent years, the company shifted their focus in sustainability and changed over multiple facilities to operate smart manufacturing. The initial capital investment has slightly brought down the production number, but Toyota carefully prepared for the industrial revolution. The company will again achieve great heights in their production as well as waste productions.
Now we will discuss our findings and our final thoughts on smart factories. From our 3 case studies, we compose a list of areas of similarities between all 3 smart factories. The 2 main similarities were the use of cloud-based data sharing and the integration of AI. Cloud-based data sharing controls networks to increase data transmission and streamline factory standards and data. This allows for the factories to be operated as a whole and allow for factory-wide monitoring to increase production rates and efficiency. Another aspect was the use of some sort of AI technology with the cloud-based networks to more efficiently optimize a sector or even a whole factory. The AI analyzes the data from the cloud and determines what can be done to reduce times and unnecessary actions. This is something that has been implemented in various stages in the 3 case studies and all being implemented at different levels. But they all focus on increasing production rates within a factory.
In addition to our analysis of current smart factory implementation in North America, Europe, and Asia, we also looked at studies that examined smart factory use as a whole. Two major areas of interest that we wanted to know more about were, are companies actively interested in further developing smart factory initiatives, and what are the concerns these manufacturers face when looking to implement? The graph on the left shows a breakdown of differing levels of smart factory initiatives for over 1,300 manufacturers between 2017 and 2019. In 2017, 24% of these companies reported that they had no initiatives, 33% said planned initiatives, and 43% reported that they had active factory initiatives. In 2019, these numbers drastically changed. 68% of these companies jumped to having active smart factory initiatives. This shows the massive growth of smart factory initiatives across the globe. The second chart shows the major challenges faced by manufacturers that attempt to implement smart factories. Top contender here, 51% of companies reported that they see deployment of integration of digital platforms and technologies as the biggest challenge. From this, we can infer that investing in additional infrastructure will benefit the implementation of smart factories. And as we said in the last slide, they primarily rely on the cloud-based data sharing and artificial intelligence. So therefore, this increase in implementation of infrastructure will benefit smart factories as a whole. We just want to say thank you for listening to our smart factory presentation. We're excited to hear from the other ones.